All right, in this video, we're going to finish the Chapter 5 review problems. We got to question 6 in the last video. Now we're going to do 7 through 12 in this video. And you might be asking, why are we doing every single review problem? How come in the videos on this channel we work so many problems? You know, a lot of times it's like we're doing the same concept over and over again. Well, I do that on purpose, and the reason is because it's the repetition is how you're going to master these concepts, absorb them, and remember them in the long term. That's why over many different videos, I'll repeat a lot of the same things. And so don't think if you're watching different videos and you're hearing me say the same things that don't be tempted to fast forward. No, every single time I say something, listen like you've never heard it before. Think about it in your head like you've never heard it before. If you do that multiple times, it's that repetition, that practice. That's how you're going to master the concepts and absorb the concepts and retain it for the long term. Okay, among freshmen at a certain university, scores on the math SAT followed the normal curve with an average of 550 and a standard deviation of 100. Fill in the blanks and explain briefly. A student who scored 400 on the math SAT was at the what percentile of the score distribution? Okay, so again, we've got the formula for the normal curve saved as an equation. And if we're assuming that freshmen at a certain university, the scores followed a normal curve, average 550, standard deviation of 100. So a student who scored 400 was at the what percentile? So we need to, since it follows a normal distribution, we're going to use the area under the normal curve to get the percentile. What percentile is this score? 400. What is that asking? That's asking what percentage of the area of the histogram is to the left of the score of 400. And the histogram we're talking about is the normal curve because that's what we're assuming the scores are. That's how they're distributed. So but we need to convert 400 to standard units because that's the areas under the normal curve. The x-axis is in standard units. So what is 400 in standard units? Well, how far it's going to be below. How far below average is 400? It's 150 units below average. So it's minus 150 below average. How many standard deviations is that? 1.5. Okay, so what's the area on the normal curve that's to the left of minus 1.5? Okay, we do this. So direct or definite integral, and it's going from, we don't know, no, we do know the z-score. It's minus 1.5 is the upper limit, and the lower limit is negative infinity. 6.7%. So this is the, I guess we could say 7th percentile. Could we round up? Let's think about that. If we want to round, do we round up or down? Well, if we say 7th percentile, then the technical 7th percentile is if you scored like 402 or something like that, or 401. So, you know, you kind of, I feel like I wouldn't want to round up here. I mean, it doesn't matter. You could say 7th percentile. But, I mean, you get what I'm saying. I'm going to put 6.7th percentile just because you could round down, meaning that, like, if this was 6.15, you could round down because if a 400 is in the 6.2 percentile, then you could just say 6 because if you're in the 6.2 percentile, you're definitely in the 6th percentile. But it's not the other way around, so it doesn't matter really. To be at the 75th percentile of the distribution, a student needs to score a score of about what points on the math SAT? All right. So we say the 75th percentile is going to be, we want to calculate some number z. We don't know what the z is. And E, okay, so now we want to solve this is equal to 75 for Z. So 0.67 is the score. All right. If you're wondering what I'm doing here, we go to the previous videos. I go into detail on all of this. So the Z score that corresponds to the 75th percentile is 0.67. So are we done? No, we want to convert that. Now we want to convert that to a score. So how do we convert that to a score? Well, the idea is it's the score we're looking for minus the average divided by the standard deviation is going to be this Z score. Right? So with that, if we say 0.674 times the standard deviation, which is 100, and then, so now we've got X minus the average is equal to this, so now add the average. 617, we'll just round down, about 617. And then I just looked on Chegg, they put 620. So it's the same, both are right, but I'm just trying to get a sense of what they're doing. So if you put 620, then like if 617 is the technical, is very close to the 75th percentile. And if you put 620, that's going to be like the 76th percentile. So it's no problem to just put 620 to make it clean numbers. True or false, and explain briefly. If you add 7 to each entry on a list, that adds 7 to the average. True. And it doesn't change the standard deviation. If you add 7 to each entry on a list, that adds 7 to the standard deviation. No. False. It doesn't change the standard deviation. If you double each entry on a list, that doubles the average. That is true. And it also doubles the standard deviation. If you double each entry on a list, that doubles standard deviation. True. If you change the sign of each entry on a list, that changes the sign of the average. Yes, true. But it doesn't, if you change the sign of the entry on a list, that changes the sign of the standard deviation. False. Multiplying by any minus one or having a minus sign multiplier doesn't affect the standard deviation. That minus is not applied to the standard deviation. Which of the following are true? False. Explain or give examples. The median and the average of any list are always close together. I mean, no, not necessarily. So this would be false. You can give examples of 1, 2, 3, 500, 1,500. So the median is 3, but the average is not going to be close to 3. I mean, especially if I can make these numbers as big as I want and really pull the average away from 3. So no, not necessarily. Half of a list is always below average. Half of a half of the data points. No, false. Because we've seen, what we learned in this chapter, or in the previous chapter, was that if you have a histogram that's not symmetrical in this way, then you'll have the median will be, somewhere here, and the average is going to have to be higher than the median, which means that more than half of the list is below average. The half of a list is always below the median. The median is the middle point as far as the list of numbers. Half of a list is always below and above the median. But we know that half of a list is not always above and below the average. The median and the average don't have to be equal. I mean, I'm not sure exactly. If we look at this example, the 1, 2, 3, 500, 2,000. Okay, the average is going to be, 300 or something like that. Well, okay, yeah, if 300 is the average, then 2 points are above the average, 3 points are below. And I could even go to an extreme. Let's put 100 million here. Well, now the average is going to be somewhere between 500 and 100 million. So now 1 point is above the average. The rest of the points are below. I think one rule you could say is that the average it will never be greater than the largest point. Like the average could never be above 100 million, or it could never be below 1. but it could be anywhere in between. With a large representative sample, the histogram is bound to follow the normal curve quite closely. No. Whenever we talked about the normal distribution, yes, in general, for any list of numbers, there's a lot of numbers follow a normal distribution, but it's not. The book has clearly stated that histograms that aren't normally histograms or lists of numbers that aren't normally distributed aren't abnormal in any way. I mean, there's plenty of histograms that aren't normally distributed. So what they're saying here, this representative sample that we take from something, that sample is, which you could think about, it's going to, if it's a large representative sample, it's going to follow the distribution of whatever the population you took that sample from. If you have some statistic and you're taking a sample of people in the United States, that's some statistic. You're at different statistics, height, age, weight, whatever, are going to have different distributions. But you can't get those data points for every single person in the United States, so you have to take a sample. Well, the sample distribution is going to, if it's a good representative sample, it's going to have the same distribution as whatever the full population distribution would be. And unless the book had been telling us that most or all lists of numbers will follow a normal distribution, which it doesn't, then this is false. Normal distributions are very common, probably the most common, and I've talked about why it's called the ideal distribution. Like it's called that for a reason, but there's a lot of situations where you have data sets that aren't normally distributed. Okay, so this is false. This is false. If two lists of numbers have exactly the same average of 50 and the same standard deviation of 10, then the percentage of entries between 40 and 60 must be exactly the same for both lists. Well, this is definitely false, because it doesn't even say that if the two lists of numbers they both have the same distribution. So with that, this is definitely false. Now you might be thinking, well, it gives an average and a standard deviation. That's normal distribution. Average and standard deviation have nothing to do with, they're not intimately related to a normal distribution. You can calculate the average and standard deviation for any list of numbers. These are just good statistics. They're very good summary statistics for lists of numbers, histograms that follow a normal distribution. But that doesn't mean that, but just because that's the case, that doesn't mean that this statement is suggesting that we have two lists of numbers that follow a normal distribution. Okay. Now, all right, what if it told us that these did follow a normal distribution? So they both followed a normal distribution. Well, not exactly, but approximately. If they both exactly followed the normal distribution, exactly, and they both had the exact same average and the exact same standard deviation, then yes, this would be a true statement. But the way we've been talking about it is that we've got two general lists of numbers that you can assume that they follow a normal distribution. It's not exact. So if you could assume that they both follow the normal distribution and they both have the same average and standard deviation, then could we say that the percentage of entries between 40 and 60 is exactly the same for both lists? No. We could assume that the percentage would be pretty close, in the same ballpark, yeah, but that they would be exactly the same? No. We've seen that. If you have a list of numbers that you assume it follows the normal distribution, and then you calculate, for that list of numbers, you calculate what the standard deviation is, or the percentage of data points are between plus or minus one standard deviation. Well, if it follows the normal curve exactly, that's supposed to be 68%. But we get is like 71%, which is close to 68. That's the idea. You might, if we calculated for these two lists of numbers, if they both follow the normal distribution and we calculated how many data points were between plus or minus one standard deviation, one might be 67, one might be 71, in the same ballpark, but not exactly the same. Unless you said they both exactly follow the exact normal distribution, which kind of doesn't make sense. How could it be that exact? Oh, it could be. I take it back. It could be. But it doesn't say that, so false. For women aged 25 to 34 with full-time jobs, the average income in 2004 was $32,000. The standard deviation was $26,000, and 0.25% had incomes above $150,000. Was the percentage with incomes in the range from $32,000 to $150,000 about 40%, 50%, or 60%? Choose one option and explain briefly. Okay, for women aged 25 to 34 with full-time jobs, the average income in 2004 was $32,000. Standard deviation was 26. It doesn't tell us anything if it's normally distributed. And 1/4 of 1%, so 0.25%, had incomes above $150,000. So that would be the 99.75 percentile had incomes above $150,000. Was the percentage with incomes in the range from $32,000 to $150,000 about 40, 50, or 60%? Well, it doesn't tell us if this is normally distributed. So to me, you can't, I don't know. Well, all right, so let's say we're going to guess. We know that income distributions usually have like a tail like this because there's not that many people that are, there's a lot of people that are way out here. There's a few people that are way out here. Okay, and so I guess they're kind of giving us the upper range. So, okay, here is probably a little more to the left. Here's the average. This would be, what is it? 32. And then, pretty much the upper point is 150. Oh, okay, yeah, we could probably figure this out because in the range of 32,000 to 150. Okay, so what do we know about the average? So in this case, the average is going to be to the right of the median. Okay, because of the average is the balance point. The median is where it's half the areas to the left, half the areas to the right. That's the definition of the median. Half the data points to the left, half the data points to the right. Well, since we've got more data points that are kind of spread out like this, then to compensate for that lever, the balance point is like here. Okay, so this is the median. All right, so we know that with this in mind, we know that this area here, we know the area between the median and 150. That's going to be, so it would be, this is 0.25% of the area is out here. So just 50 minus 0.25, 47.75% is the area between the median and here. 47.75%. Okay. The area between 32 and 150 is going to be less than that for sure. So it can't be 50. It can't be that. So it's going to be, well, there you go. Okay. Yeah. So it's got to be 40. Between these three options, it's got to be 40. And, I didn't draw this to scale. You could probably say the averages are more separated, but you can see that this area here is a good chance that's like 7.5%. It could, maybe that is drawn to scale. Maybe that's good, but that's about 7.5%, right? So take 0.25, you start with 50 because you know the area above the median is 50. Start with 50, subtract 0.25, and subtract like 7.5, and you get this 40%. That's the area between the average and 150. One term, about 700 Statistics 2 students at the University of California, Berkeley, were asked how many college mathematics courses they had taken, other than Statistics 2. The average number of courses was about 1.1. The standard deviation was about 1.5. Would the histogram for the data look like 1, 2, or 3? Why? All right. About 700 Statistics 2 students at Cal Berkeley were asked how many college mathematics courses they had taken, other than Statistics 2. The average number of courses was about 1.1. Would the histogram for the data look like, okay, interesting. I don't know. It seems like more, I don't know if this is a statistics question. You need to understand you need to be a college administrator, but would this be so you're just you have these Statistics 2 students in like this big auditorium, and you're doing a survey, how many math courses have you taken outside of Statistics 2, college math courses? And so if you think about the way these tails work, like you're going to have a bunch of students, like, okay, for this situation, you would have like an average here, about 1.1, and then you would have like students out here that would be saying they've taken 4 or 5, but not many. And the rest would be saying like, I've taken no math courses before this. So to me, you would have You know, this is not, this is another thing to consider here. This is not, you can't answer 0.5. You can only answer like 0, 1, 2, 3. So this would mean a bunch of people said 0. A bunch of people said 0, a bunch of people said 1, a bunch of people said 2. And then there's a small number of people saying like 4 or 5. It's kind of like, that's the idea. I mean, some said 3 or 4, but like that's the idea. Or so, I don't know. Here, no way. So you had like everybody, most people in the class saying they've taken, like, this doesn't make sense. The average here would be somewhere there. That's 1. So you have people saying they've taken a negative amount. This doesn't make sense. Okay. Here, average 1.1. This is like kind of like a normal distribution. Standard deviation is 1.5. 2 standard deviations is 3. I mean, I don't know if you'd have this either. Yeah, I guess it would make sense that you'd have a group of people that are with like 0, 1, or 2. And then you've got like, you know, a select smaller number that puts like 4 or 5 college math courses already. But it's not just like it's like one person doing that. Like you can have outliers in a normal distribution. You can have outliers. But like also you can't really, but you couldn't have outliers in the negative direction though. That's what this would suggest, right? You can't have like for a normal distribution or something like this, you could have outliers that say they put 5 or 6 classes. But then you could also have outliers that say they have like -2. That doesn't make sense. Here, that's not the case. There's no outliers that said -2. There's outliers that said like 5 or 6, not negative. So this one here. In 2005, the average score on the math SAT was about 520. However, among students who took a subject matter test, the average score on the math SAT was about 624. What accounts for the difference? I mean, I don't know. You know, some of these questions, it's like, I feel like they can make you think too much because, you know, I need to be a school administrator to answer this. But okay. Obviously okay, what could they be trying to, as far as what we've read in the book, what could they be suggesting here? So it's like only the average changed, but not necessarily the standard deviation. If that's the case, then it's like you just adding a number to every single number in the list. I'm not sure if that's what they're going for here. But yeah, you can think about it that way, right? If you've got the students that didn't take a subject matter test and the students that did, if the standard deviation didn't change, just the average changed, and it's like you added a constant to each number in the list. Kind of in general you did that. So for whatever reason, the students that took a subject matter test were either smarter or more, in general, were either smarter and more prepared or something. But then it says there's just math, though. So they're better in math. I would imagine that the scores, even in non-math, would go up. If you compared from the subject matter level tests, people who took subject matter tests to people who didn't take subject matter tests, if you compared the scores even in non-math, the average would go up. So for whatever reason, at this school or whatever, I don't know what this is, if people that take subject matter tests are more prepared or they're just smarter. They're more prepared for the SAT or they're just smarter or something. I think the idea they're going for is think about what it means when you have 2 different lists and you just add, in general, you just add the same constant or subtract the same constant to that list. It's just a shift. You go from like a histogram like this, and that you go to another histogram like this that just shifts. That's it. Standard deviation doesn't change, but it doesn't really say anything about the standard deviation, so I don't know. All right, that's it for chapter 5.